The Technical AI Safety Podcast is supported by the Center for Enabling Effective Altruist Learning and Research, or CLR. CLR, known to some as the EA Hotel, is a nonprofit focused on alleviating bottlenecks to desk work in the effective altruist community. Learn more at clr.org. That's CEEALAR.org. Neurosymbolic Reinforcement Learning with Formally Verified Exploration by Greg Anderson, Abhinav Verma, Isil Dillig, and Swarat Chaudhuri. Abstract. We present Revel, a partially neural reinforcement learning framework for provably safe exploration in continuous state and action spaces. A key challenge for provably safe deep RL is that repeatedly verifying neural networks within a learning loop is computationally infeasible. We address this challenge using two policy classes, a general neurosymbolic class with approximate gradients and a more restricted class of symbolic policies that allows efficient verification. Our learning algorithm is a mere descent over policies. In each iteration, it safely lifts a symbolic policy into the neurosymbolic space, performs safe gradient updates to the resulting policy, and projects the updated policy into the safe symbolic subset, all without requiring explicit verification of neural networks. Our empirical results show that Revel enforces safe exploration in many scenarios in which constrained policy optimization does not, and that it can discover policies that outperform those learned through prior approaches to verified exploration. I have with me Greg Anderson. Greg Anderson is a PhD student at UT Austin working at the intersection of machine learning and formal methods. He is particularly interested in developing tools and techniques which can analyze machine learning systems to guarantee safety. Thanks for coming on the show, Greg.
Thanks for having me.
So take us through the abstract. At a high level, what's this paper going to do?
So the big idea here is to bring the kinds of formal safety guarantees that we like to have for traditional software into the world of machine learning. We've seen recently that reinforcement learning is this really powerful tool, and we can use it to learn how to do all kinds of interesting things. But in a lot of cases, we really need to be able to guarantee some kind of safety property. The easiest thing to imagine here is, for example, you have a self-driving car and you don't want it to crash, right? And if it crashes, that's going to be a big problem. Traditional machine learning algorithms really aren't set up to handle this kind of guarantee. They only work by sort of exploring and seeing what happens. So if you are going to let your car explore until it crashes, that's not really a feasible way to do things in this domain.
Right. So I guess that gets into my next question. What was the status quo of RL that you saw before you wrote the paper, and what are the shortcomings with it that your paper is addressing?
So the big issue here, we already mentioned, is one of safety. Now, there had been this work, and I know you talked about this in a previous episode, on how to bring this kind of formal safety to RL using, for example, shielding. And that's great, but shields have a couple of problems. The most notable one is that the shields themselves tend to have very low performance in the sense of sort of in the machine learning sense. So what happens is whenever the shield has to sort of interfere to maintain the safety property, that causes kind of a big performance hit on how well your agent is going to do. So the goal with this work was basically to try to take this idea of shielding, but now train a shield and a network concurrently so that you can sort of get better performance while maintaining the kind of safety guarantees that you want.
Cool. Awesome. So something I noticed when I did that episode on Safe RL via Shielding, the paper by Konigoffer, Ehlers, Al-Sheikh et al., which you cite in this paper, was that shields are something that we would wrap around states. We would wrap around the environment. Whereas here it looks like shields are something that we are wrapping around the policies. Am I understanding that correctly?
Yeah, so both views are accurate. It just kind of depends on how you want to interpret it, because what ends up happening is the shield is sitting between the agent and the environment. So you can sort of take a perspective of, if you're looking from the agent, then the shield is something that's going to change your actions before they get sent to the environment. You can also sort of take a view of the shield and the neural agent being considered together as a single policy, and that's sort of what we do in this work.
I see. Okay, that's very interesting. So listeners may recall that specifications from which shields were synthesized in the 2017 paper were written in linear temporal logic, or LTL. Did you have to use LTL in this application or not?
We didn't do that for our experiments. We only considered properties that have this kind of state exclusion form. So we basically define some set of unsafe states, and then we want to show that you never enter these states.
Right.
In principle, nothing is sort of stopping you from considering LTL properties here. It just requires a more advanced way to do the kind of verification that we need to do.
Okay, cool. We're gonna get more into that set of unsafe states and like where that comes from a little bit later. But now I want to really get in the weeds and just get all of our terms really defined. So for real quickly, we're talking about continuous state spaces and continuous action spaces. Just real quickly, could you recapitulate the distinction between continuous and discrete state and action spaces?
Yeah, when you have a discrete space, the idea here is basically that there's some kind of separation between different states. So you can think, for example, of like integers. There's, you can choose state 1 or state 2, but there's nothing in between. When we talk about continuous spaces, what we mean really is that you can select actions, or you can be in states that fall on sort of a whole range of possibilities. So you can think, for example, that if your action is a real number, then that's continuous. If it's an integer, then that's going to be discrete.
Right. Totally. It's great. So it says that Revel, which is the implementation of the framework that comes with this paper, is called a partially neural RL framework. So what does partially neural mean?
So what we mean by that is that we're taking this sort of standard deep reinforcement learning framework. That would be something that's purely neural, where your agent is just a neural network. And what we're doing here is we're taking that neural network and we're now augmenting it with some other information. And we're going to use that information to try to get sort of extra benefits that you can't get from the network alone.
Okay. Cool. Extra benefits that you can't get from the network alone.
So I guess to be specific about that, one of the problems that we see with neural networks is that they tend to be very large. They have a lot of parameters, and even though the structure at kind of a micro level is relatively simple, it's all just linear transformations and activation functions. If you want to try to sort of analyze the behavior of the network as a whole, it's very hard because there's just a lot of parameters. It's sort of the tools that we have for doing analysis don't scale to the level of networks. So the idea here is that we know the network is really good at giving us good performance. So now the shield, which is this extra component that we're going to mix in, is going to guarantee safety while we get to sort of still maintain those performance benefits.
Got it. Cool. So a policy is a function from states to actions, and that, modulo whatever machinery you need to make it probabilistic. What is a symbolic policy?
So the symbolic policy really is somewhat loosely defined, but really it just means this is a policy that gives us, the kinds of benefits that we were just talking about. So in our case, this might be it might be a decision tree. It might be like a traditional program, like you would write in whatever your favorite programming language is. But the point here is just that the symbolic policy is somehow understandable or analyzable in a way that neural networks aren't.
Right. So it's like human readable for free.
Yeah.
Yeah. So its output is something like a program or a decision tree. It's literally its codomain is like the space of programs or something.
Well, so the policy is just a program, the symbolic policy. So it's the same thing. It's just a map from states to actions. But rather than being represented as a neural network, which is really hard to work with, it's represented in some simpler format.
Ah, I see. So, and then if I'm thinking of a policy as a table, how do I get to symbolic policies from there?
So, the thing about continuous action spaces we mentioned earlier is you can't really have these tabular policies.
Ah, I see.
Because your action space is always going to be infinite, yeah.
Okay, perfect.
So instead, you're going to have some function, right? And then now the idea is this function can be represented in different ways.
Of course. That makes total sense. So then we have neurosymbolic policies.
Mm-hmm.
And they differ from symbolic policies how?
So this is the blended thing we were talking about a little bit with the partially neural framework.
Right.
A neurosymbolic policy is some combination of a sort of neural policy, something that's represented as a neural network, with this symbolic policy. And so how you do that combination can change depending on your goals, but in our case, it's this kind of wrapping or shielding, where you have the neural policy, and then the symbolic policy is going to sort of guard what the neural policy can do. And the whole thing taken together, this network plus the shield, collectively we refer to as a neurosymbolic policy.
Great. Fantastic. So I'm going to get into some of the formal verification terms and concepts here. For every subset of states, I construct reachability sets using the reachability functions that are computed recursively. An important piece of this computation is the p hash function, I'll call it. Or P hashtag P whatever you want to call it.
P sharp is what we would call it.
Oh, you would call it P sharp?
We have been calling it, yeah.
P sharp, that's great. So is the P sharp function, which defines worst case bounds on environment behavior. So I want to know more about how it is that we know P sharp. It seems like having to know it a priori is a limitation of this strategy.
Yeah, I would say that's probably the most major limitation of the strategy. To a certain extent, if you want to do formal verification, you have to know something about your environment. Because if the environment can just do anything, then there's no way you can ever prove something, because the environment could just take you to an unsafe state at any time with no warning. So you have to have some kind of model of your environment. And where this actually comes from is a little bit, in our implementation, this is just given. We're assuming that somebody has written this worst case model for you.
Right.
But yeah, that is a major limitation of the tool, and it's something we're interested in looking into more.
Cool. Later when we're talking about next steps or other possibilities, I want to maybe talk about, synthesizing P star or learning P star or some fancy stuff like that. Just pure speculatively. So you have So what is this inductive invariant? I'm guessing induction is a natural property because the reachability functions were computed recursively. Is that related to?
Yeah. So an inductive invariant here is sort of a classic way to prove safety in these kinds of transition systems. The idea here is that I want to come up with some way to separate the initial states where the system can start from the unsafe states that I don't ever want to get to. And so the way I'm going to do that is I'm going to compute some set of states, which is the inductive invariant, and that set of states has to satisfy three properties. It has to include all of the initial states, it has to exclude all of the unsafe states, and if I start at any state in my inductive invariant and take one step, I should stay inside of the invariant. So that's sort of where the induction comes from.
Ah, great.
And collectively, those things give you a proof of safety.
Okay, cool. So you have this function safe from policies to essentially propositions. and you have to implement some proof solver, which you refer to as an oracle, which finds a proof that's safe of pi. So what does this proof look like, and would you be able to translate into English in a meaningful way?
Yeah, so the inductive invariant itself is a proof, because the idea is, if an invariant exists and you start in any of the initial states of the system, then basically you can never move outside of the inductive invariant, right? Because your initial states are inside of the invariant, and if you start in the invariant, you cannot step out of it.
Right.
So this invariant gives you a proof of safety already.
Totally.
So, how exactly you want to represent that invariant is going to depend a lot on sort of the shape of the policies you're interested in, stuff like that. But that's sort of the basic idea.
Cool. Is there a way you could maybe give an example on in some kind of toy environment of what a phi, what a proof, what a inductive invariant would entail?
So, yeah, let's one of the environments we use here is an adaptive cruise control setting. So basically the way that's set up is the agent is controlling some car, and this car is following another car. And so there's a natural safety property here. You don't want to crash into the car in front of you,
right, but
you do want to sort of keep pace with the car in front of you, or maintain some distance. So you can imagine, for example, if I have, let's say, a controller which is designed to, let's say it's very conservative. It never gets closer to the car in front of me. So, if it observes that the car in front of me is slowing down, it's immediately going to slow down, and maybe we'll just say it never speeds up, right? That's a very conservative, that's not a good policy, but that's a policy that is safe. Mm-hmm. So the invariant here is basically characterizing some set of states that you can't leave. So, for example, in this environment with the controller I just mentioned, if you start out, or if you are at any point going slower than the car in front of you, then you can never reach a point where you're then speed up and go faster, because you don't speed up.
Right.
And if the car slows down, you slow down. So that's kind of the idea here, is that you're coming up with just something that characterizes a set of states that you cannot leave. Great.
So that's the formal verification end of things. Now on to the learning side. So we know what gradient descent is. It's an iterative way to trace a ball as it rolls down a hill. What is functional mirror descent?
So mirror descent is a really general sort of optimization technique. So I just want to talk about it a little bit specifically in the context we use it here.
Great.
Basically, the idea is I have this space of policies that I want to do optimization in. And for our case, this is shields. I want to find the best shield. And the problem is that shields don't have gradients, because they're in this format. They can have if then else's, for example, and those things aren't differentiable. So the idea of mirror descent is, I don't have gradients on my shields, but I have this sort of augmented space of, in our case, this is neurosymbolic policies. And so what I'm going to do basically is take a shield, lift it into this space of neurosymbolic policies, and in this space I have approximate gradients. I still don't have exact gradients, but it turns out I can approximate gradients in a reasonable way. So then I can do gradient descent in this space of neurosymbolic policies, and then I can sort of project this back down into the space of shields. And so what that's letting us do is basically use gradient descent to optimize these shields, even though they don't actually have gradients themselves.
Fantastic. We're going to get into a little bit more detail with a couple of those steps in a couple questions from here. So you're working with two classes of policies, G and H, with G being a subset of H. and G is provably safe policies, and H is the neurosymbolic policies. Mm-hmm. So what exactly is the property besides provable safety that the policies in H without G are like distinguished?
Well, so the first thing is both of these classes are provably safe policies. Because G is giving you the shields, so that's sort of the purely symbolic policy. And then H is this class of neurosymbolic policies. So you can think of that as like the network that's been wrapped with a shield. So you're always getting safety in both of these classes. The reason that you need H here is because H also gives you approximate gradients.
Okay, so approximate gradients is the thing that H has that G does not.
Yes.
Great. Okay. So I'm still thinking about shields as policies that have been wrapped in something. Right? Is that basically accurate? And when we use the word shield, we're referring to policies that have been wrapped around.
So when I use yes, the shield is something that is wrapped around the network.
Wrapped around the network, so, but is it wrapped around the policy?
Yeah, the network is the
network
policy,
is the policy. Indeed, that makes sense. I got it.
Or rather, okay, I guess to be slightly more clear, the network defines a policy, and the shield defines a different policy. So when we do this wrapping, what we're doing is we're combining this purely neural policy with this purely symbolic policy, so that we end up with this one object that sort of gets the benefits of both.
I see. Now it's clicking for me. So I noticed there's this third class, F, of policies that you have to predefine. So I'm wondering, is F as a class similar enough to H that these policies can be synthesized from a specification of H? Or are you really hand-rolling policies in F?
F is just the class of purely neural policies. So,
okay.
Yeah. The idea, when we say that it has to be predefined, really what we mean there is you just have to pick an architecture for your neural network.
Oh, great. That's what we mean. Great. Picking an architecture for the neural network. So given a G from G and an F from F, we also need an inductive invariant phi. There's a conditional expression that computes for us an item in H. And what this is saying is it's saying if F is safe according to phi under P star, then use F. But if it's not safe according to phi under P star, use G. Is that basically the idea?
That is, yeah. So that's basically the idea. The one important thing here is that this computation is done sort of on a per state, per action basis.
Right.
So, H is this entire conditional, and then that conditional you can think of as being executed at any particular state and action that you want to consider.
I see. That's an important distinction. So we're not going to get too granular here, but I am going to want to step through the lift update project loop. So lift, right? So lift update project is the main loop in the algorithm. Lift just produces an item of H without G and consumes an item from G in an inductive invariant phi. And as I understand, this is done by learning, right? So is it surprising that you can learn something with guarantees like safety or invariance?
So the guarantees here are all coming from the shield. So your learning sort of doesn't have to be good in order to get you any guarantees, because no matter what you learn, you're always going to be wrapping it with this shield. The point of this sort of imitation learning that we're doing is that in order for the mirror descent framework to work out, when we lift a policy in G into H, we need the resulting policy in H to behave the same as that policy that we started with in G. So that's the point of the imitation learning. The idea is like, I have this symbolic policy or this shield, And I want to find a neural network that's going to behave the same as that shield, because that way when I put them together, I'll get a neurosymbolic policy that behaves the same as my shield. And that's just important for mirror descent. Got
it. So for the update step, this to me looks a little bit like gradient descent. The computation of the item in H is represented as a tuple G phi F. It gets iterated into the tuple G phi F minus some learning rate times the gradient of the cost of H. And this remains safe because via the conditional expression, it would fall back to G if P star showed that the iterated function was unsafe. So is that basically correct?
Yeah, that's accurate. We're using gradient descent to update. Basically, we're only updating the neural component of this policy,
right?
Using gradient descent in sort of a standard way, and then because of the way the shield works, you can make whatever changes you want to this neural component, and you'll never sort of break safety.
So how do you know learning won't get stuck just picking the safe branch of the conditional over and over again?
In theory, that can happen. So first of all, empirically, we didn't find that to be a problem. And there are sort of some intuitive reasons that you would expect it to not be a problem, primarily because basically the network should be getting better rewards if it doesn't go into that behavior. So sort of just by gradient descent, it will sort of learn to stay in this safe region. But, theoretically, there isn't really anything preventing that from happening. It's just that it doesn't come up in practice.
Okay, got it. So I just want to get a slightly more detailed picture of what an element G from the class G would look like. So each G is based on a list of partitions of the state space. And these partitions are these linear predicates. What are linear predicates as opposed to predicates?
It's just some predicate that might include a linear expression over the state variable. So the easiest way to think about this is I have some set of state variables. Let's say it's a vector x. I can take a dot product of that with some set of coefficients, and then I can compare it to a constant. And we're either going to have... So basically, you can think if you have some vector of coefficients, this is basically like, the dot product of C with X is less than B, for example. That's a linear predicate.
Indeed. Great. So an item G is made up of of a list of G sub i's, and each G sub I only acts on one partition of the state, of the state space. Each G sub I is linear, right? So would an example G sub I be like some dot product or just some like linear combination of...
Yeah.
Of what?
So I guess first of all, this specific class of shields, this idea of having piecewise linear functions sort of isn't inherent to the framework, but this is just what we use for our experiments.
Okay.
But yeah, that being said, for this specific choice of shields, each piece here is just some linear transformation from the state space to the action space. So it's basically a matrix.
Great. Got it. And how would that have to be adjusted for probabilistic to make G like more probabilistic?
So I'm not sure that you would want to have your shields be probabilistic, primarily because the point of the shield here is to be easy to analyze.
Right.
And analyzing things gets a lot harder if you start introducing sort of distributions and stuff like that.
Yeah.
Of course, there are things you could do. You could imagine, for example, rather than just producing a particular output, you could imagine producing like a mean and standard deviation using, linear functions. But I don't know that that's necessarily something you would want to do in this context.
Okay, cool. So really quickly, you have a section on like theoretical analysis of the method. Are there any highlights from that section that you're particularly excited about?
Yeah, so the really interesting thing is we have this convergence result, which basically says if you run the algorithm long enough, you're going to find something very close to the optimal shield. But what I think is really interesting about that is you mentioned earlier this problem of getting stuck, basically always choosing the safe branch. Our theoretical result actually shows that while that can happen, your sort of the quality of your convergence, that is to say sort of how close you get to the optimal policy, is directly proportional to how often you end up getting stuck in that, or I should say inversely proportional to how often you end up getting stuck in those safe branches. So there's sort of this theoretical result that shows that if you don't have to invoke the shield too much, then you'll converge, and even if you have to invoke it a little bit, you still converge most of the way, which I think is pretty interesting.
Oh, okay. You still converge most of the way.
So the way to think about this maybe is there's some kind of reward for a given policy, right? As you know, that's standard in RL. There's always some kind of reward that you can give to a policy, and basically the difference between the reward for the optimal policy and the reward for the policy that you actually learn, this is called a regret bound. We can show that the regret bound is not too big, and we can also show that it's, roughly speaking, proportional to the amount of times this shield has to intervene.
Fantastic. That sounds like a useful result, that the regret bound is proportional to the amount of times the shield has to intervene. That sounds very useful. So moving on to the empirical section and the experiments, what were the performance bottlenecks in this strategy?
So the biggest thing here is that coming up with shields takes a long time. And to a certain extent, that's not really surprising because, this kind of formal analysis is just a very hard problem to solve, especially in complicated environments. So, yeah, by far the biggest bottleneck here is the shield synthesis algorithm.
Right. So the oracle, the proof search, isn't necessarily a bottleneck.
Well, so the proof search sort of has to go in parallel with the shield synthesis. Yeah.
Okay. It has to go in parallel.
Well, what I mean by that
is
just that. Yeah, what I mean is just that because you have to find a shield that's going to be safe, it's sort of like your shield synthesis algorithm. When it comes up with some candidate shield, it always has to check whether that's safe or not. And so that kind of thing. Yeah, basically the search for a proof is always interleaved with the search for a shield, because you always have to check every shield that you would like to return and see if that shield is actually safe.
So is the oracle synthesized at runtime?
No, so the oracle is just there to. It's just some method for checking whether a shield is safe.
Right, got it.
And it's, it can be based on all kinds of different things depending on what system you're in. In our case, we have these piecewise linear shields, so you can just do, you can either do something with SMT solvers, and you can do something with sort of abstraction-based techniques, but that just comes down to sort of what works out the best in your environments and in your sort of setting. Right.
So Revel is spending 87% of its time on shield synthesis. And the sense I get is that you're not too surprised, or you weren't too surprised about this.
No, I would say that's
basically expected.
I would say that's pretty much what we expected.
Cool. What else should I have noticed about the experiment section?
So the most interesting thing about the experiments, I think, is that we have this comparison between Revel and DDPG, which is like a totally standard reinforcement learning algorithm.
Yeah.
And what happens is the performance of the policies that we end up learning is, in most cases, not really substantially worse than DDPG. And, you have to keep in mind, DDPG is not considering safety at all in training. So what's happening here is that we've sort of managed to add this layer of safety without really sacrificing very much at all in terms of the performance of the policies we're getting.
So I want to zoom out a little bit. I noticed earlier that the set of unsafe states that the learner must always avoid is given a priori in the definition of the MDP. And you already said that if you want to verify anything, it has to be something that you do know a priori. But I want to talk more about this limitation. How much of this strategy is recoverable if we don't know what's unsafe a priori?
So it depends on what kind of assumptions you can make. Of course, if you have let's say your safety signal here, let's say, is some Boolean, right? Your state is either safe or it's not safe. In that case, there's really not much you can do unless you know the set of unsafe states beforehand, because the only way you would find out if a state is unsafe is to explore it, is to go to that state. But there's other stuff you can imagine doing. For example, if your safety is not just, this Boolean notion of safe or unsafe, but instead you had some kind of continuous safety signal, a state can be various levels of safe, then, it's not clear exactly how, but you can imagine doing something here where by looking at the safety in the current state, you can maybe try to estimate safety in sort of states you haven't seen yet. Yeah, it's not totally clear how you would do that, but there's definitely some possibilities there.
So I want to kind of go through a scenario on this point, because I feel like to keep labor down, right? We don't want human experts hard coding too much, right? Mm-hmm. We'd want to develop tools that could be used to help define these sets easier. Mm-hmm. Right? So, with that in mind, can you imagine working for a self-driving car company and you have to define not driving off the road in a efficient way, looking at looking at some data of some visual input of roads and highways, and algorithmically marking states as unsafe. Is that kind of feasible? Is that how you would envision that?
Yeah, that's definitely one possibility. You could imagine, for example, training a classifier in some kind of supervised learning setting to say this location is safe or not safe. And that's definitely one area that you could explore. The problem you run into here is that now you're kind of pushing the verification problem onto whatever is generating the model, right? So if you have some function that's going to give you the set of states that are unsafe, well, now, yeah, you can verify with respect to that set of states, but now you also need some way to be confident that the set of states that it told you is unsafe is really accurate and complete.
Yeah, of course. So on at the level of the social problem, marking states unsafe is not at all solved, because even when you have a human expert hand rolling the unsafe states, there's still a trust issue. If you trust that human to be absolutely correct about that.
Yeah. So we just assume for our work that whatever we're given is correct. But of course, yeah, that's all down to whoever wrote the specification.
Indeed. That poses a whole set of problems that I think is very, very interesting. But it might be out of the scope of this podcast to solve. Right? So maybe I'll so moving on, unless you have any further comments on that.
No.
there's the literature on out-of-distribution robustness that deals with the difference in model performance from training to testing, or from a controlled environment to an uncontrolled environment. Do you think there's anything there that would help with this question of needing to know unsafe states a priori?
So, my understanding of the out-of-distribution robustness work is that it mostly focuses on this idea of basically identifying inputs that are not similar to any of the training data. Is that more or less accurate?
Yeah, as far as I know.
So, I think that kind of work could be useful for basically identifying states where you need to exercise extra caution because you don't know very much about them. It's a little bit more related to there's this other work that's been going on in CFRL that doesn't take the kind of formally verified hard constraints approach that we use, and instead they take a much more stochastic kind of soft look at this problem.
Like within epsilon safe.
Yeah, well, epsilon safe, or they'll do this idea where they don't assume a model, but a priori. But what they'll do is they'll sort of learn some kind of safety model as they go, and then try to sort of reduce the probability of visiting unsafe states over time. There's all this kind of work, and so I think this idea of estimating sort of how much confidence you have in a prediction is probably more relevant to that line of work.
Interesting. Yeah, that makes sense. Okay, so I want to fast forward to artificial general intelligence, where it's like whatever, like pick your favorite like sci-fi scenario. But assuming that today's known paradigms like reinforcement learning and iterative descent algorithms end up getting us all the way there, if that makes sense, to a world, and in this world, the general AI systems are running amok, but they haven't destroyed the world; they're peacefully coexisting with humans. So, in the best case, what role do you think this paper would have played in the path to that state?
So, what we're doing here is really just proving that you don't do certain things, I guess, to put it at a high level. So, of course, this, we already talked about this a little bit, but this depends on somebody to write these specifications. But, there's, if you want to say, take it back to sci-fi for a second, there's potential, I guess, to use these kinds of ideas for, this kind of like laws of robotics type stuff, like if you can write down a set of things that you want to guarantee never happen, obviously we don't scale to that kind of level yet, but if you can write down a set of things and you want to say, I want to guarantee that these things never happen, then there's some potential to use these kinds of tools.
Interesting. I'm not familiar enough with the literature that kind of, tries to do the real life version of the 3 laws of robotics to think of interesting examples of these specifications kind of being deployed at that level. So what about the other way, right? Like, what if there's maybe not to do with general AI exactly, but what if there's this like disaster, this like Chernobyl moment for AI, that where like something catastrophic happens with AI systems. Can you imagine that this paper would have played a role in that scenario?
So the only thing I can think, and this comes up all the time in kind of formal verification settings, is that this comes back to this problem we keep mentioning of who's writing specifications and how good they are at it. But the only sort of thing I can imagine happening here is that you write a specification, you train a system, And because you've done it with this kind of formal verification, you have a lot of confidence, right? And of course, if your specs don't take into account really all the bad things that can happen, then you may believe that you have a safer system than you really do. This is sort of a classic problem in formal verification. This comes up all the time.
Mm-hmm. Yeah, that's definitely something. So what about if instead of this is something I'm talking about with a potential team at the AI Safety Camp 5, is what if we used techniques like shields to wrap like types of behaviors instead of specific behaviors. So if we could classify certain types of moves like contextually as like say cooperative in multi-agent games, as opposed to more defective, would we be able to use shields to, or put it really simply, can you imagine some Prisoners of Dilemma bot where a shield was used to make the bot stay cooperative?
So, let's see. A shield really is a very general thing, so I don't think that would be impossible. Because I guess all you really need here is, you have an agent that's going to propose some action in some state, and so whether your shield is specific to that particular agent or is sort of a more general thing, if you have a shield that constrains the behaviors that you care about, I think you can apply it, as broadly as you'd like. So I think that's not impossible.
Very interesting. Very interesting. I'm going to think a lot more about that. So Greg, we're wrapping up. We got 3 more questions here. If a listener wanted to replicate this paper, do you have any advice for them?
Okay, so, well, first thing, the code for this paper is available. So
right,
that would
right. The Revel implementation is on GitHub.
Yeah. Aside from that, I think the paper does a pretty good job of explaining, or obviously, I wrote the paper. I think it's pretty good, but I think from the paper you can follow the high level implementation, or the high level sort of framework. What's going to be sort of challenging is how you want to write this projection step or the shield synthesis algorithm, and how you want to sort of implement your verification oracle. It's hard, I guess, to give general advice because that's going to be something that depends heavily on the exact class of shields you want to use. But I would probably just look at the code on GitHub to get some idea of at least how we did it.
Yeah, and I looked at that just a little bit. Could you briefly say, like, what parts are in C++ and what parts are in Python?
So roughly speaking, the formal verification stuff is mostly done in C++. The machine learning stuff is mostly done in Python.
Right, that makes sense. Okay, cool. So what's next for this kind of line of work? Are you still in this line of work, or are you like going in other directions?
So I'm still working on this. There's 2 directions that we're really interested in. One of them we already talked about quite a bit is this idea of model learning. Of course, having a model given to you by some human is not the most efficient thing and perhaps not the most reliable thing. So we would like to see if there's ways to do this with some kind of model learning. There's a lot of questions left to be answered there. The other direction, which is somewhat more concrete, is to look at broader classes of shields, basically to come up, as I was mentioning, with better shield synthesis algorithms and better verification oracles.
Great. Is there anything else you'd like to get out to readers of this paper?
So I guess the high level takeaway of both of this paper and of kind of this whole body of work on neurosymbolic or partially neural learning is that we've seen for a while now how powerful neural networks can be, and sort of how much they can help us solve problems that weren't really feasible prior to the advent of deep learning. But what we're sort of increasingly learning now is that neural networks do have some deficiencies. You can't just rely on networks. So I think that what we're going to see, and to my mind, what is the most interesting research direction right now, is, what are the ways that we combine these networks with tools from traditional software engineering, tools from other sort of areas of CS and math, and how is that eventually going to give us, the kinds of desirable properties that traditional software has that networks sort of don't have at this point.
Sounds awesome. Sounds really interesting. Well, my guest today has been Greg Anderson. Thank you, Greg, for coming on the show.
Thank you for having me.
Music by Alex Kulik. Thumbnail image by Max Weil.